Okay, hello and welcome back. Yes, we are ready to move on now to the next section. What we are going to do in this video is the last piece of theory and definitions that I want to give you before we start looking at actual calculations that you might come across in the matric examination. So let's start looking at things that you should remember from grade 11, Newton's second law, and I'm going to work with Newton's second law and the law of momentum as you see it down here. Okay, so let's just get a blank page going. Right. Oops. Right, let's get a blank page going. We like some blue color there today. Newton's second law, which I will represent by Newton 2. Newton 2, right? It says the following. It says um, if a net resultant force is acting on an object, it will cause the object to accelerate in the direction of that force. And this acceleration is directly proportional to the force and inversely proportional to the mass of the object. And then in symbols or in a formula we say F equals ma, right? Where m is the mass of the object, and a is the acceleration. Right. Now, let's see. We've got the law of momentum, right? The law of the momentum, we've seen it previously. We've spoken about it not too long ago, maybe about 20 minutes ago. And we said the law of momentum in symbols is actually F net delta t is equal to delta p, where delta p is the change in momentum. Right. In general, we're talking about one object here at a time. Okay. And of course, it can also mean the change in momentum of the system. That's when we're dealing with the net force related to the system. Okay. So what if I told you that the two above are related or they are equivalent? Okay. Show that the two formulae, the above formulae, are related or are equivalent. Okay, let's see how we can do that. So I'm going to let's use a little bit of, let's stay in black, and let's see how we can relate them. Right, let's start with this one here. F net, let's just make it F delta t for the sake of brevity, is equal to delta p. That follows that F is equal to delta p over delta t. Well, delta p is the mass of the object times the change in velocity, right? Well, let's just make it v final minus v initial, because you've previously seen it written as such, divided by delta t. And then that again is the following. That is really let's see if we can just make that longer. There we go. That is really m, and any final minus initial is what we represent by a delta. So that's actually delta v divided by delta t. Now if you look closely, this part over here, delta v over delta t, is something you may remember from grade 10. Right? Delta v over delta t is something you remember from grade 10. That acceleration, let's write it here, a is equal to delta v over delta t. And this is something you need to be able to do, to convert the law of momentum into Newton's second law. And we can then say that that is m multiplied by this delta v over delta t, which is a. And therefore we get, of course, F equals ma. And so that's how we can see that the two are related, right? Newton's second law is related or equivalent to the law of momentum, because we can take this one, manipulate the formula a little bit, and make it look like that to show that the two are indeed equivalent. Okay, so the next part I want to quickly look at and mention to you is this over here. that impulse is defined as the change in momentum of a system. So you can see that this is impulse. The change in momentum is actually F net delta t. Okay, it's not F net, it is not delta p over delta t, but rather it is F multiplied by delta t, or it is the change in momentum. So this is impulse, and so is this. This is impulse, and then this here is also impulse. Okay, I think I'm writing like a kindergarten here. Impulse, right? That's impulse. That's each of these things are different formulae that represent the impulse. So there's two things about it. One is that it's not a mathematical quantity, but rather it's a natural one. And then secondly, an external resultant force, if there's a resultant force in an object, relating Newton's second law to what we've just learned now about the definition of impulse, we will find that if there is a net resultant force, an object will undergo a change in momentum. Now, the reason the object will undergo a change in momentum is if we talk about Newton's second law, F equals ma, right? A change in momentum really means that the velocity of the object is changing. And if the velocity of the object changes, then it really means that there's an acceleration, because change in velocity denotes that there's acceleration. And if there's an acceleration on the object, then it means that there's a net resultant force acting on the object. So according to the law of momentum, we say that if there's a resultant force acting on an object, it will cause the object to undergo a change in momentum. And now there's a certain relationship that relates to the time taken, the net force, and also the change in momentum, right? And this is the impulse relationship. It is very useful in explaining some of the everyday applications that are used in various apparatus to reduce injury and risk. Now that's just important so that you know where it can be used. Now, I'm not going to waste a lot of time giving you examples right now. Rather, I'm going to go through a few question examples in which we will answer questions related to the impulse relationship and the net force, whereby you can see where the examples exist.